Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. Today's episode is brought to you by Mitsubishi Electric Cooling and Heating. Imagine perfect comfort in every room of your home. Well, it's here now. A modern, zoned comfort solution from Mitsubishi Electric Cooling and Heating. Each room can be an oasis with its own temperature control and filtration, and the systems are so quiet, you'll barely even know they're running. All you'll experience is comfort, the way it should be, tailored to you. And you can condition only the rooms you want and save money by turning off the rooms you don't. Forget about that old central system and step up to modern comfort, control in every room of your home. There's a smartphone thermostat, whisper quiet operation, and over 40% more efficiency than central heating and air. Enjoy the modern comfort of zoned comfort solution from Mitsubishi Electric. Modern comfort reinvented.
Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello everybody. Hello and welcome back to the Building Science Podcast. I'm Christoph Irwin, your host, and I'm here as always with my producer, Michael Walker. Today we are talking about heating and cooling indoor spaces using VRF technology, VRF mechanical equipment. The term VRF stands for Variable Refrigerant Flow, and it's a very descriptive term that is pointing to the core functionality and the core functional benefit of these systems, which is efficient delivery of part load performance. A little bit of jargon in there, but part load means when it's not peak load, like when it's not as hot or as cold as it ever gets where you live. And efficiently delivering part load performance means efficiently delivering partial capacity. So if you buy a 2-ton system, what if you don't need 2 tons? What if you need half a ton, right? So VRF allows that to happen. And it allows that to happen by varying the refrigerant flow. So refrigerant is the heat transfer medium, and if I vary the amount I deliver, then I'm varying the amount of heat or cooling. And keep in mind, cooling is just absorbing heat.
And just to clarify, this episode we're going to talk about the big why, why to use VRF. And we'll have another episode where we're going to discuss how to actually implement VRF technology on your projects.
Yeah, what we want to do here is to bring the why the world is looking at VRF, why VRF technology is accelerating its capture of market share in the US so dramatically. We want to bring it down on this episode into terms that are very simple and understandable. So yeah, as Michael said, our goal today is first to help you understand what VRF is and why you should care about it. And that's important. We're in a culture that's rich with information, but sometimes less rich with knowledge and wisdom. So we want to point to that. Why are we looking at VRF? And then next, maybe not more importantly, but equally as important, the next episode will be on how to use VRF in your projects. And in this part, we're going to cover the rich variety of components and how to work with your engineer. For your architects in the room, VRF technology is essentially a new palette of colors that you can use to deliver conditioned space to your clients.
Whoever thought HVAC could be so poetic?
So we'll also talk about controls and design considerations and working with installers. And we have a lot of experience here at Positive Energy with working with VRF, and not just the nuts and bolts of how to do a design, that's actually the easy part, but how to get a design delivered that is less easy, how to get it built. Okay, so even when we organize it and filter it that way with these 2 episodes, there's still a lot of ideas to cover. So let's dig in. Heating and cooling is obviously a core function of any home or building, right? We all know this, right? The decision on how to do that is really impactful. And it's one that unfortunately often does not get made or does not get made explicitly. We can't avoid making the decision. It happens on every project, but we can avoid responsibility for making the decision and hand it off to someone else and assume that that person has the owner's interests in mind. In today's market, that's a big assumption and one that I don't think is often valid. Rapidly changing building enclosures complicates the answer to what is an appropriate mechanical system.
So you mean the tighter the building gets, it poses a larger question about how to condition it.
Yeah, absolutely. So we have men and women out there that have years of experience delivering heating and cooling to buildings, and when they look at the building, it looks the same, but thermodynamically it's radically different. So their system needs to respond to a radically different set of conditions, but that's not obvious. In the best case, what we have is an informed owner fully engaged in making this key decision. We are lucky at Positive Energy. We do a lot of custom residential work, and getting access to the owner means typically a husband and wife. It's not a board of directors or complicated thing like that. Other decision makers, right? We have this interlocking set of stakeholders in this decision. So we have the project architect, who might hold implicitly the owner's project requirements, or OPR, or maybe they're written explicitly. That would be great. Next would be the MEP engineer. That's typically more on commercial. We're very lucky that we do residential MEP, and we have a lot of very thoughtful architects that work with us that recognize that just because it's a house doesn't mean you don't need to plan the MEP. So the GC could have this decision. If the GC gets the decision on how to heat and cool, they're probably going to turn it over to their mechanical contractor, and if it's turned over to the installing contractor, it's almost certainly going to have some implicit bias toward what they're familiar with.
So there's a hierarchy from owner down to installer.
Yeah. Even within the installing contractor's company, there could be someone in the office that's extremely well-versed at making this decision, and then eventually when it gets to the job site, what gets installed or how it gets installed might not have been given the oversight that it needs. This episode today is for all of those stakeholders, and the goal is to make sure that we're all aware of VRF mechanical systems, and we're very clear on what they are, how they work, and why they're likely to be a good choice. So VRF, it's a mature technology, it's reliable, it's quiet, it's energy efficient, it's easy to install and maintain, and it's really appropriate for either new construction or retrofits. It's appropriate whether it's for your home, your light commercial project, or your own personal skyscraper.
I think I got a couple of those tucked away somewhere.
So yeah, it's appropriate for all types of buildings. And I want to stress that it's mature, right? We're going to talk a little bit about the history coming up, but it's been around for many, many years. It's been in the U.S. market for about 30 years, and it's just now starting to catch on. In fact, in that regard, the U.S. market is playing catch-up to the rest of the world. And that's probably somewhat due to the costs of energy here relative to other markets. And
there's some other political factors at play, and we have a podcast episode about that, actually. That was one of our very first episodes, so go back and check that out.
And we're not trying to talk about the election, though.
Of course.
Let's not get started on that. Beyond politics, there is also the reality of, if the installer is familiar with doing, technology A, well, then that's what they're familiar with. There's going to be a bias toward that. So, again, the core benefit for VRF is this efficient part load performance. This is very important, the ability to deliver variable amounts of heating and cooling, because the load, the temperature outside relative to in is constantly changing. So we'll talk about that again. VRF is also a potential answer to broader economic and societal goals like net zero or net positive energy buildings.
You guys catch that?
And of course, this societal benefit of net positive energy, it can't be solved one-handed, right? You have to pair an uber efficient VRF system, or there are definitely other good types of mechanical systems, but you have to pair them with a fantastic enclosure, and that is quantifiable, right? You want a low thermal flux density, something like 10 BTUs per hour per square foot or less. So keep track of that on your projects. VRF can be a game changer even in New England, even in Alaska, right? I want to make this important point early on in the podcast. These are not your grandpappy's heat pumps that we're talking about, right? The heat pump industry got a black eye early on because the delivered heat specifically was above the thermostat set point temperature. So it was heating their space, but it was below skin temperature, so it felt like a cold draft. So that is not the case now. VRF systems, they can cool very effectively in very hot climates, and they can also heat with high output temperatures, upwards of 120 degrees Fahrenheit, 130, during very cold weather, down into the single digits Fahrenheit for full capacity, and even the negative single digits for meaningful part load capacity.
We're talking about Fahrenheit here.
Fahrenheit, yeah, it's a big deal. Yeah, to make sure it makes saying it in Fahrenheit. Going through, I guess, the highlights again, what we have is the ability to deliver variable amounts of heating and cooling. We also have the ability to integrate these systems with hot water production. This is a very big deal. And unfortunately, right now in the US market, manufacturers, are you listening? This is mostly available in commercial. Generally speaking, we have the opportunity to have a system where in the summer, I'm using this heat pump to pump heat out of my conditioned space. And what do I do with it? I go reject it outside, which is great. But wouldn't it be great if first I could reject it into hot water? That's possible when we embrace integrated VRF systems. In the winter, in that same scenario, I have a heat pump water heater, which is fantastic, right? So this integration of domestic hot water with space conditioning is a very big deal and one to keep track of. We're also talking about net zero, net positive energy. What we're talking about there is the fact that the clean energy economy is underway, right? We as a global society are reinventing the way we power our world, right? We have for generations powered it off of fuels, wood, coal, fossil fuels, right? Now we're looking at powering it off of a technology, right? Wind and solar are not fuels, they're technology. The fuel is the sun far away. So, bottom line there is globally we are not in the process of creating a gasified grid based on renewables. This means that if you want to be forward-looking and want to go off-grid or want to have a net positive energy building, one long-term view is to realize that it needs to be all electric, and that means heat pumps for heating. We've talked earlier with Robert Bean, and we know about exergy efficiency, and that's a big deal, right? To burn natural gas at 3,500 degrees Fahrenheit and use it to heat and cool a space to 70, 75 degrees Fahrenheit or water to 120 degrees Fahrenheit. That's a ridiculous waste of energy. So we talked about VRF being the name, but actually the name is something that we need to take some time to dig into here because I guess implicitly negative for the penetration of this technology is the confusion associated with what it's called. Particularly when it comes to public awareness, right? To illustrate the need for some clarification, let me just explain that VRF equipment is called mini splits, multi-splits, ductless, and VRF, right? So there is the three-phase, single-phase split, but generally speaking, what we have is we have equipment that delivers heat and cooling to spaces. So the most common name, mini split, well, I guess you could say it's both descriptively inaccurate if you're thinking about the full line of VRF. It is mini for a couple of reasons. One is in the 1950s, when these systems were first introduced to the market, they were actually physically smaller with what they were competing with, which were these newfangled massive window units. So what we had was a situation where in the U.S., central cooling was actually very rare. Central heating was happening, but central cooling was rare. So people, I think we all know this, air conditioning came into buildings or into homes, particularly through wall units, which were loud and big. So the Japanese in the 50s introduced a product that was smaller than these physically, and it was split. The loud piece was split so that it could go outside. Small piece was inside on the wall. It's also mini in today's world because it's smaller in terms of tonnage or in terms of heating and cooling capacity. The whole tonnage thing. Why do we say a ton of air conditioning? It's because we're silly. I've covered that on previous episodes. I'll leave it for now, but it's still split, right? So what we have are, in the US market, you can buy a package unit, like you can buy a big window unit or a small window unit. Those are package units on one package. You can buy package units that sit on the roof of a commercial building, right? As soon as you split the piece that needs to communicate with the outdoors from the piece that provides heating and cooling to the indoors, now you have a split system. In the US market for typical split systems for homes, you can have a 5-ton, a 4-ton, a 3.5-ton, a 3-ton, a 2.5, a 2-ton, a 1.5-ton, and that's it. Right? So you can't get any smaller than 1.5-ton. And for the good equipment like the 2-stage, you really can't get much smaller than a 2-ton. With a mini split, ducted or ductless, important there, ducted or ductless, you can do a 1/2-ton, 3/4-ton, 1-ton, 1.25-ton. So you go smaller. Mini means it's smaller, split means it's split. But really the core benefit is not that it's smaller and split. The core benefit is that it has variable capacity and that you can put multiple indoor units, whether ducted or ductless, onto one outdoor unit. So this feature of putting multiple indoor onto one outdoor is a multi-split, right? So I would like to hear us all say either VRF, or when it's a multi-split, to call it a multi-split. And if it is a one-to-one system, then we could call it a mini-split. So that is the emerging de facto norm, right? But it's slow to get through. So what we have right now is something like manufacturers are saying, if it's above 6 tons, we'll call it VRF. And if it's less than 6 tons, we'll call it various things. So I think it's easier for the market if we just recognize that any mechanical system that's based on the fundamental variability of refrigerant flow has VRF technology at its core. Let's just call it VRF. But that's my opinion. All right, so just one more little point to make. There's at least one manufacturer that also has variable refrigerant flow equipment that refers to it by a different acronym, which is VRV, which stands for variable refrigerant volume. And of course, the volume of refrigerant can vary if the flow varies for a certain time. So, bottom line here is there's lots of different names for it. Don't get confused. Don't let it dissuade you. Don't let it slam you or your client's brain shut. Do endeavor to speak accurately, and let's move on, right? So names aside, VRF technology is not some mind-blowingly complex thing. All HVAC systems, all vapor compression-based systems are based on simple, reliable, predictable physical laws that engineers can use to design reliable systems that work for years and years.
That's a mouthful.
Simple, reliable laws. Yeah, so don't believe marketing rhetoric to the contrary that, these are the droids, these are not the droids you're looking for kind of thing, right? All right, so that covers the name. Doesn't exactly make it clear, but basically VRF, multi-splits, mini-splits, ductless, they're all leveraging variable refrigerant flow, and you should endeavor to learn more about them by continuing to listen and to listen to the next episode that's coming up. When it comes to the history of VRF, right, or the current market position, it is the primary system technology that's dominant in Europe, Asia, Australia, many other parts of the world. Here in the U.S., it is accelerating its penetration into the market. We might be growing from small single-digit percentages, but we're growing fast. There's lots of room to grow and lots of layers and good reason why this growth is happening and will undoubtedly be continuing. Again, VRF addresses and resolves that thorny issue. How do we deal with part load conditions? Part load, again, are those conditions that are normally what your home and mechanical system are dealing with. And we currently have technology that is designed for peak load conditions. So we have equipment that is optimized to perform at conditions it rarely sees. Somewhat getting into the history of VRF, it's long, and I'm going to keep it very short, right? It was first developed in the 1950s in Japan, quickly spread throughout Asia and elsewhere. Many places where energy costs, maybe refined technology and other factors had higher market prominence in products than knowing what's familiar. I don't really know why it spread throughout there and took so long to come back to the U.S. The U.S. actually was involved very early on in the 70s with variable capacity compressors at the precursor to NREL. And then the U.S. canceled its energy crisis, and this technology has somewhat languished since then. But Asian manufacturers entered our market in the 80s, and they did so without really much acceptance or much market penetration, partly due to the fact that they did not bring adequate market infrastructure to penetrate the momentum of, our market's familiarity with, quote, normal systems, lack of manufacturer support and training, inability to maintain and get parts. These are all big problems. They're all resolved today. Being straight about that, right? In Austin, they're resolved. In most parts of the country, there are manufacturers that are available to support VRF. There are myriad manufacturers of VRF systems, right? I think to keep this podcast product neutral, I won't rattle them off, but I could probably rattle off 10, and if I thought about it more or researched on it, probably 20 or 30 different VRF manufacturers. Common names, you would know them. One bellwether that may be worth noting is that ASHRAE, right? So ASHRAE is the group of engineers at their headquarters in Atlanta. One of the technologies they chose to heat and cool their building was, in fact, a VRF multi-split. So we talked about having a basic conceptual relationship with how we heat and cool our our buildings, and I was tempted to go into how the vapor compression cycle works. So we did a podcast on the basics of the vapor compression cycle a while ago. I think it was when I was driving to go kiteboarding and the audio was not perfect. I would love to go through that again with you, but instead I'm going to refer you to some external sources. So there's going to be a link on the show notes here to an ASHRAE article that is very well done on how to talk about the basics of heating and cooling through vapor compression. And then Martin Holliday at Green Building Advisor has done some great stuff. And of course, our buddy Allison Bales at Energy Vanguard. And so, but I'm going to give you the most basic, please don't take this as talking down, but let's just say at this level, right? This reminds me of how Richard Feynman would talk about physics, right? So let's talk about a basic conceptual understanding of heating and cooling equipment, right? Let's, as a starting point, talk about machines in boxes. And in fact, let's just talk about boxes, right? So typically we have one box that's outside and one box that's inside, right? So the inside box is doing what, right? We know it's giving you something that's hot in the winter and it's giving you something that's cold in the summer, right? It's usually giving you cold or hot air, but it doesn't have to. It could be giving you cold or hot water. And then the outdoor box, it's doing the opposite, right? So if it's an air conditioner, right? The indoor box is giving you cold, the outdoor box is putting out heat. In a heat pump mode, the indoor box is giving you hot, the outdoor box is putting out cold. And so we have gas furnaces, but without digging too much into it, go back and listen to the episode with Robert Bean, I think just a couple episodes back. Basically, we should stop as a society using gas for heating water or air, right? Cooking, I get it, not going to go there. But basically, if I need to reject heat to the outdoors, all I need to do is make the outdoor box hotter than the outdoor air. And let's say 40, 50 degrees hotter, and it'll dump heat into the outdoor air just fine, right? So 40 to 50 degrees hotter. Imagine you're in a nice 70 degree house and you go outside and it's 20 degrees outside or 30 degrees outside. That's a big difference, right? So same thing here. You have an outdoor box and it's plenty able to reject the heat from inside your house into the outdoor air. Now, these indoor boxes, right? So where are these indoor boxes? Well, they can be in a closet. They can be in your attic. If your attic's unconditioned, well, that's a very silly place to put a box that's trying to make 40 degree air. But we do it. But whatever. So it's a box. It can be in your house. It can also be mounted directly on our wall, mounted directly on the ceiling. It can be embedded in the ceiling so that there's a little bit showing, a little grill showing, kind of like a window unit. It can sit on the floor like a radiator style box. It can be mounted on the wall low, right? All of those applications do not require ducts, right? What you need to do is you need to put a box there and you put electricity to it, a refrigerant line connection or a water line connection, and a drain for the condensate that you're going to make if the air is humid, and you're done. No ducts, no plenums, no diffusers, filters, filter chassis, all those things go away. And the associated costs. And there's something to say about that. If you really want a high quality, high MERV filter system in your space to get good indoor air quality now, you are going to want a supplemental system. And similarly, if you're going to want a system that is paying attention to whether it's too humid or not, you're going to want a dedicated dehumidification system, right? So VRF systems can absolutely handle the heating and cooling flawlessly. They can do a darn good job of drying the air, but not as good as a dedicated dehumidifier. They filter the incoming air, but not as good as a HEPA filter chassis could. And they also need support when it comes to ventilation air. Right, so boxes outdoors, boxes indoors. The boxes indoors can be ductless. They can also be ducted, right? So this means you put a plenum on a box, which is just another box, and then you connect trunk lines and runouts, or you connect, the duct kraken to your plenum, which is, an intestinal-looking bunch of ducts. Actually, don't do that. But so you can have ducted equipment, and you can have ductless equipment. Either way, you have boxes indoors, boxes outdoors. The boxes indoors can be mixed. You can have a ducted system each, right? This would be typical. We have a ducted system for the central core, which is the living room, dining room, kitchen. You have another ducted system for the Jack and Jill kids' bedrooms, right? And then a third one for the master. That's very typical. Then you might have a fourth ductless unit, like ductless now in the garage for when you're out there and working and it's too hot or too cold. So there we go. We had all 4 units connected to one outdoor unit. All 4 units were completely independent of each other. They could be any 3 of them could be off, and the 4th one can be on, or any 2 of them could be off, right? Any one of them that's on can be asking for different levels of heating or cooling. Caveat there. Residential equipment, they all have to be asking for either heating or cooling, right? So I could have one at 70 degrees and one at 78 degrees as long as they're both in cooling mode. Commercial equipment, and not too long from now in residential equipment, if you listeners ask your manufacturers for this, right, we can have simultaneous heating and cooling in our homes. Right now we can only have it in our commercial buildings. And that's a big deal, right? So just touching on that, simultaneous heating and cooling is another function of VRF mechanical equipment. And what that means is, let's do the home example. Let's say it exists and you're doing simultaneous heating and cooling in your home. And you have a 3-story house and it's very hot in the attic or on the 3rd floor where I'm up there in my man cave, and that's my office, and I have a big video or something like that. So it's getting very hot. All the heat in the house from cooking is coming upstairs. Yeah, let's say it's winter and the house is being heated. All the heat's going to come upstairs. I might very well want to have my house, my zone, my 3rd floor man cave cooled. So I want my unit to be in air conditioning mode. Well, check this out. If I put my unit into air conditioning mode, that means I'm absorbing heat from the space. I could take that heat, put it into the refrigerant, and it could go down to the air handler in the basement and shed that heat down there. So basically my refrigerant now is just moving heat from place to place. So it's very elegant. The point being that you have multiple indoor boxes. They can be mixed or matched, ducted or ductless.
And to piggyback on that, to Christoph's point about a new palette of colors with VRF equipment, those indoor boxes aren't all the same thing. There are different form factors that can work with different types of architecture and actually expand your ability as an architect or a builder to pull off some really creative stuff and still provide excellent heating and cooling for your clients. And that's a big deal.
That's a huge deal, yeah. And in fact, what you're hearing, and I won't apologize for it, but you're hearing an experienced, educated, geeky person, me, who really cares about technology that goes into homes and buildings. I'm actually focused more on homes, and I long to have the same equipment that is available currently in the residential world that's currently available in the commercial world. So yeah, you're getting my distortion there, and you're absolutely right that VRF compared to normal, right? So let's do that. I just did that house, right? It had 3 ducted indoor zones and a ductless unit in the garage. Let's say I'm trying to do that with conventional equipment. To pull that off to the same level of functionality, I either have 4 indoor units connected to 4 separate outdoor units. So you should think, man, what a lot of embodied energy to bring all those copper coils and all those separate compressors to exist outside my building. I either have that, or I do an air-based zoning system, right? So that means dampers, air-based dampers. And air dampers are an energy efficiency non-starter. They're typically a comfort problem. I know of many times where they can be done right. There's tremendous technology with variable speed fans. But generally speaking, you still are spinning a large fan, albeit more slowly to get less air when it's part load. So I got that massive fan spinning, and I still have the need to control all that in a simple way, which is not as elegant. So what we really need to know is that VRF technology is as normal and sensible as the gears on a bike that we change when we go up and down hills, or my favorite metaphor is the accelerator pedal in our cars or trucks that we use to maintain a steady speed, right? So what if our vehicle didn't have an accelerator, right? Those of you that are driving, imagine this: floor your car and use your ignition key, right? Not only would it be perilous and scary, but it would waste a lot of fuel. It would cause extra wear and tear on the whole engine and drivetrain, leading to more frequent and costly repairs. And kaboom, that's exactly how conventional heating and cooling equipment works. It's on, floored, until that's not the right thing, and then the only option is to turn it off, and then pretty soon that's not the right thing, and the only option is to turn it back on, where it's floored over and over and over, wasting energy, causing wear and tear the whole time, right? Not to mention unstable comfort conditions. What we're basically saying is, let's say it's summertime here in Austin, and my system turns off because it's met set point. House gets hot until picks typically 3 degrees above set point. Now system comes back on. Typically it's oversized for various reasons, and it crushes the cooling load. Now it's too cold, 3 degrees below set point, system turns off, back and forth, back and forth, back and forth. Right? With VRF equipment, we are definitely staying within a 1 degree band of temperature, right? The system has the accelerator pedal. Just like the hills and valleys you drive your car over, the hills and valleys of the constantly changing weather are occurring, and that is what your heating system and cooling system needs to be dealing with.
And it's worth saying, I grew up, and probably many of us grew up, without knowing what was possible thermal comfort wise. But when you actually experience a VRF system over long amounts of time, like I do in our office, it is a noticeable difference than anything I've ever experienced in my life.
Yeah. And my favorite moments are when clients come in and we get to say, yeah, there's our VRF system, and they say, okay, go ahead and turn it on.
It is on.
I love
it's that quiet.
Yeah, so that's a big, there's something I want to touch on here. 2 things, right? One is this dehumidification, filtration, and ventilation, right? We still need, depending on the owner's project requirements, we're still going to need a dedicated dehumidifier. VRF equipment definitely has the ability to effectively enter dry mode and dehumidify. They currently don't control the system based on that. The filters that are used on the ductless equipment, depending on the owner's project requirement, might need a supplemental particulate capture system, right? If someone wants HEPA, they're not going to get it with a ductless wall head. Ventilation, most or many of, and we'll talk about this on the next episode, many of the indoor boxes that we were talking about have the ability, even ductless ones, some of them, have the ability to provide ventilation air, meaning we connect it to an outdoor opening and bring in filtered outdoor air and mix it with our system. These are not magic one-size-fits-all boxes, but they come very close. So there's more to say. As with anything, the more you know, the more there is to know. And I want to just touch here on the fact that because air conditioning systems are around you all the time, heating and cooling systems, I should say, are around you all the time, we start to not notice them. And I really want to encourage you all as people and as professionals to perk up, to get curious, to pay attention. We breathe all the time. We need healthy air in our homes all the time, right? So, in fact, if your life's goal is a sense of ease and well-being for yourself, your family, and your society, then it could be argued that today's topic, right, like heating and cooling equipment, is at least as important as deciding on your next tech gadget purchase, if not more, or your next vehicle, right? So we spend 87% of our time in buildings.
That's
right?
a lot of time.
Yeah, and so what are we doing all the time, right? We're breathing, the 200 pounds or so of air you're going to pull into your lungs today. They're like food, right? You're actively taking it into your body, into your blood. I just looked this up with my daughter. If you take apart the human body and you count the different atoms that are in it, 2/3 of them are going to be oxygen. So we're basically 66% oxygen. Where do you think that came from, right? From the air. Take a deep breath. I'm a little stopped up today, but I just pulled, right, there you go. Michael just pulled air out of our studio here. It went into his lungs. Some of it crossed over into his blood. And now he exhaled, and the carbon dioxide comes back out and goes into the air, right? So he is an internal combustion engine. And he has his air intake and his exhaust pipe.
Fueled by tacos.
Yeah, fueled by tacos. We're not gadget interfaces, relying on our fingers and our eyeballs to exist, right? We are physical, tactile beings immersed in a richly complicated world of physical and sensorial impacts, right? We talked about this in IEQ. But I really want us to as a group of people, as you guys listening, just, enjoy it. Look around. This is not theoretical. Become curious, aware, and interested in the world around you. So we're getting close to the end here, but anyone introducing the topic of VRF to you would be remiss if they didn't introduce 2 core features of VRF, which are the electronic expansion valve, EEV, or the variable capacity compressor, right? So those two components are really where the rubber meets the road and make a difference, and I am not going to be remiss in talking about them. So we talked about the fact that VRF stands for variable refrigerant flow, and that the varying amount of refrigerant enabled us to absorb or release varying amounts of heat to our space, right? So how does that work? Well, not as complicated conceptually as you might think. Think of a hose spigot, like a faucet handle, and think of something like an atomizer, like a mister outside a restaurant, or maybe those old-timey perfume bottles that go poof, poof, poof. So that is an electronic expansion valve. The valve is regulating the amount of flow, so that's the spigot, and what it does is it expands the fluid into a mist. It takes the refrigerant from a column of liquid and it turns it into liquid droplets. In so doing, it creates more surface area on the liquid has more surface area as a bunch of little droplets compared to a cylinder, for instance. And so the surface area is where the rubber meets the road in the I'm absorbing heat or I'm releasing heat. I'm doing it backwards. Let's stick with air conditioning. So the droplets are going to absorb the heat. They're going to change from liquid to vapor. That is the magic of a vapor compression cycle, which is a simple, reliable law of physics. And I'm not going to go farther. Hold me back.
You guys are welcome.
So that's the EEV, right? You have a spigot connected to something like a mister. Very simple. One more thing about the spigot. This spigot, though, has the ability to change the amount of flow very rapidly based on microprocessor control. So hundreds of times a second. Someone will be very busy over at the spigot receiving commands. But this allows for very precise control of superheat and subcooling. Again, I'm not going to go there, but those are essentially what engineers use to design these systems to make them reliable and efficient. And if we can control to very precise tolerances, then we can get very efficient equipment. The other piece is the compressor, right? So we have this variable amount of refrigerant being released, and it is a cycle. It needs to happen over and over again. What do we need to do? We need to compress a varying amount of refrigerant back into a liquid. To do that, we use a variable amount of compression. This is where the gears on the bike come in, right? So we have a compressor that is typically plugged into our electric grid, which I think we all know operates at 60 cycles per second, 60 hertz. And that's H-E-R-T-Z, not a H-U-R-T-S. So 60 cycles a second, and we run motors at that speed and things like that. Well, we don't always run at that speed. So it's very much like your bike. If you want your legs to be pedaling with the same amount of force at a steady cadence, but you'd love the back tire of the bike to spin a lot faster when you're going downhill and a lot slower when you're going uphill. So this variable capacity compressor is accomplishing that function here. There is the temptation, let's say, for manufacturers to think that adding an EEV, also by the way called an LEV for linear expansion valve sometimes, and a variable capacity compressor, that's all they need to do, and then they have a VRF system. There are a host of ninja tricks associated with the refrigerant volume and keeping the oil separated. There are also, typically with the Asian VRF manufacturers, myriad meaningful upgrades in terms of, let's just say, computational fluid dynamics is one, right? So how does the air move through the indoor and outdoor unit? Well, with typical American units, probably, who knows? But some of these Asian units, the only outdoor space for the family will be on their balcony, and that's where their VRF outdoor unit is. So they've been motivated to work very hard to make sure that as air moves through that outdoor unit, it does it in a smooth, quiet, efficient way. And this is with fan blades, this is with controlling the path through the outer unit. Same thing on the indoor unit, right? We have variable pitched fan blades. Man, there's so many opportunities to dig in deeper that I want to talk about, but we're getting pretty deep into this podcast. So a metering device and a variable capacity compressor, those are the heart and soul of the matter. But just doing that is not enough, right? You can't take your VW Beetle and take out the gas motor and put in electric motors and some batteries and suddenly have a Tesla, right? So there's a lot to making a sophisticated high-performance VRF system.
So this is a lot of information. Let's get back to what the core of this issue is, which is why should you care about VRF? Why should anybody care about or use VRF?
Well, if you're making a decision about how to heat or cool a house and your goal is to heat it efficiently and reliably in a way that recognizes that this piece of equipment that you're buying is going to last 20 years or so, then you don't want to purchase the pinnacle of a regressive technology today, right? So I would encourage us to remember that technology often changes, and there are times where the public needs to be aware of that and help the transition occur, right? We could get into the myriad market forces. In fact, I'm going to dig into just one more, which is SEER.
Please do.
Just very short. So SEER stands for SEER, and it's the rating metric that we are given as a public to decide how efficient an air conditioner is, right? So this SEER or SEER, it's essentially meaningless when you talk about a VRF system, right? Because SEER implicitly has one set point that it rates at. So it's basically like saying, when your engine's floored, what is your efficiency? And you can bet that a lot of the conventional equipment manufacturers have done everything they can to make sure that their system is efficient at the SEER rating point. And by the way, SEER has assumptions on static pressure, which is the duct system it's connected to. It has assumptions on the fan's power levels. None of these things are accurate, right? It doesn't pay attention to moisture control. There's no characterization of part load performance. It is absolutely useless to compare the SEER rating from a VRF system to the SEER rating of a conventional system. And I really want you to hear that, because a lot of times it's not heard. It's also not heard in a lot of the software modeling tools, right? You know, the only input you get, let's say on, I shouldn't say which ones, but the only input you get on some of the tools is SEER. That's how efficient my heating and cooling system is. Well, if you're going to put VRF into that, you're not going to give it credit. So giving it credit, let's wrap up. What is it that we should be noticing it does? Well, it meets this core functional requirement of efficient part load performance. That's huge. That alone should do it, right? It is mature. This technology is not new. There's an irony here, right? So a lot of the conventional American companies are getting into variable capacity equipment. It is essentially their top of the line technology in all their product lines right now. And it's new for them. And they're putting it into their old form factors with possibly without the amount of CFD modeling going into it. And so you'll get a client that says, well, I trust manufacturer A. I've always had them in my house, so I'm going to use their VRF equipment because I don't want to be the guinea pig and use this crazy stuff from Asia. Well, funny thing is that they're the guinea pig for the crazy stuff from America, and they chose not to use the very mature, refined technology from Asia, right? And so I would love, and in fact, a lot of this stuff is in fact built in this country, right? Engineered elsewhere, but built here. And I'm not going to dig into that aspect of it. But there, you see, the larger the continent of knowledge, the longer the shoreline of topics to dig into. So variable capacity is huge. This technology is extremely reliable. It is extremely quiet. It is extremely energy efficient. It offers the ability to integrate hot water generation. It has the ability to, compared with a good enclosure, to promote net positive energy operation and even off-grid or microgrid performance. In that sense, it aligns with this clean energy economy. So the last one is this ability to, the fact that it's microprocessor controlled, and this is less in just a VRF issue, but VRF equipment allows for increased information flow, which internally helps it to stay very efficient and to provide excellent comfort and reliability. It also provides external signals for for the industry, for the installing contractors to use to repair or diagnose repair on your system, right? So this is, again, what I'm getting at is your air conditioning system can get on your Wi-Fi signal and send its diagnostic data to your installing contractor's phone or computer or their office, and they can find out what's going on without driving to your house. I mean, they could call you and say, this failure is about to occur, or they could look and say, oh, I noticed the pressure here is increasing, their filter is getting clogged. Let me call them and suggest, or let me go do the maintenance. So just the way old cars, when they broke, you had to go through somewhat of a trial and error diagnostic procedure, but current cars, they have a computer, you plug the scanner in, it tells you what's going on. Same thing with mechanicals. That is a very good thing, and ironically, it's also something that causes some resistance for market acceptance because it's new and it's very different. So let's see, wrapping up this list of features, we have this expanded palette of colors for designers, right? We have the ability to have multiple different form factors, as you said, Michael, for these boxes, right? Some of them are conventionally shaped, right? So the installers are very familiar with installing that type of box in a house for heat pumps. VRF supports that. You can put units above, you can take units that are very thin, 8 inches tall and roughly 30 inches by 30 inches, fully ductable, full static pressures. I'm getting into a little bit what's going to happen next time. So yeah, just think if you're an architect or a builder or a homeowner and you want to be able to be sure that your mechanical system is not burdened by the nooks and crannies of the building you would like it to fit in, then VRF is a fantastic way to do that. And of course the ductless systems help with that. And the very last topic that I want to stress is this comfort topic, right? And of course I mean thermal comfort. I mean the ability to deliver steady temperatures inside your house. Keep in mind when we talk thermal comfort, we cannot exclude the role of the enclosure. But when it comes to the mechanical system role, the VRF system does it more effectively. It's delivering what we want more effectively than conventional equipment. And also when we talk about comfort, we need to talk about sound, right? These systems are extremely quiet. So wrapping all that up, I hope that this episode has helped you to become more familiar with what VRF is, and I hope that as you travel through the days ahead, you will become a little more curious and engaged because you will see it all around. And I hope that you come back and listen to the next episode where we talk about the specifics of these boxes and how to put them into your project.
Thanks for listening.
Take care, everybody.
Today's episode is brought to you by Mitsubishi Electric Cooling and Heating. Imagine perfect comfort in every room of your home. Well, it's here now. A modern zoned comfort solution from Mitsubishi Electric Cooling and Heating. Each room can be an oasis with its own temperature control and filtration, and the systems are so quiet you'll barely even know they're running. All you'll experience is comfort, the way it should be, tailored to you. And you can condition only the rooms you want and save money by turning off the rooms you don't. Forget about that old central system and step up to modern comfort. Control in every room of your home. There's a smartphone thermostat, whisper quiet operation, and over 40% more efficiency than central heating and air. Enjoy the modern comfort of zoned comfort solution from Mitsubishi Electric. Modern comfort reinvented.